So good morning students. Today we are starting with ISC Physics paper 2, that is practical, and today our first practical we are going to deal, and that is to find the focal length of a given convex lens by no parallax method as it is given on the board. So step by step I will explain. First of all, I will explain what is no parallax method, what is parallax and how to remove parallax, how to find the rough focal length of a given convex lens. First of all, I just want to tell you the apparatus required for this particular experiment, and that is an optical bench. Here we are using an optical bench of 1.5 meter, that is 150 centimeter. You can use of 1 meter also, and if suppose you don't have an optical bench, then you can use a tabletop also. But one thing you need to be sure that when you are taking a tabletop, it has to be parallel with the surface wherever the table is kept. Or if suppose you are using an optical bench, so first of all you need to sure that optical bench, its bar must be parallel with, I repeat, its bar must be parallel with the tabletop. That is very, very important. So the apparatus required for this experiment is an optical bench, two uprights where you are going to put the pin, and if pins are sharp, pin has to be sharp and identical, and if it is not sharp, I suggest you can use any pen also, because 0.5 mm pen, its nib is very sharp, so that also can be utilized, but both has to be identical. Then next is one upright for holding the lens, and a half meter scale, that is to balance, to find whether the optical bench is at a equal height from the tabletop or not, or for any other purpose also, and a given convex lens. Okay, so to do any experiment, first of all we need to understand its process, that exactly in after completion of the experiment, means like finding the value of u and v for 5 or 6 observations with the help of given apparatus, and by following the given procedure, we need a particular formula to find the focal length. For this method we have 3 processes. Data will be same, but by using the same data we can find out focal length of the given convex lens by 3 different processes. To explain that, our first process, by using the lens formula 1 by f equals to 1 by v minus 1 by u, and here I have used in place of minus 1 by u plus 1 by u, because it is already I have written that u is always going to be negative, so that sign convention I have used, and here the formula is 1 by f equals to 1 by v plus 1 by u. Now multiplying v throughout the equation, we got v by f equals to 1 plus v by u, and v by u is nothing but magnification m. And then finally, by exchanging the subject of the formula, we got m equals to v by f minus 1. And if suppose we will compare this given equation with the equation of a straight line, that is y equals to mx plus c. So by taking v in the x-axis and m in the y-axis, we can plot a graph. The graph will appear like this somehow. The graph will appear somehow like this if we will plot graph between magnification and image distance. Then by finding the reciprocal of its slope, we can get the focal length. But one thing we need to be very sure, so many videos are available in the YouTubes, but the precautions are hardly explained in those kind of videos. So here I will tell you, when you will plot the line of best fit for the given data, you have to be very much sure that the line drawn must be intersecting the y-axis at minus 1, because if you see the equation, there we are getting m equals to v by f minus 1. So minus 1 is the y-intercept. So as much close you will be, your line will be intersecting y equals to minus 1, that much close or that much accurate data you are going to get. So this is your first method. Second method is, if we will change the subject of formula to 1 by v, the equation equation we are getting 1 by v equals to 1 minus 1 by u plus 1 by u. So if suppose we are taking y as 1 by v and x as minus 1 by u, so which slope is equals to plus 1. Which slope is equals to plus 1. So here we are getting y 1 by v taken in y axis and 1 by u taken in x axis. So we will get the graph somehow like this. So in that case, slope we are getting this we will get y equals to means that this angle is 45 degree. So y we are getting, in slope we are getting 1. So by getting this, wherever the graph is intersecting or the line of best fit is intersecting the y axis, that we will get f equals to 1 by y naught, that is the focal length. Now the third step. For the process third, simply you plot the graph between u and v, u in the x axis and v in the y axis. Then the nature of the graph, somewhat you will get this. After that, what you have to do, you draw angle bisector for this from the origin, wherever it will intersect the graph. From that point, suppose it is intersecting at M. From M you can draw a perpendicular to x axis and to y axis. You will find that OA and OB, whatever you are getting, they are coming equal. So if you have to find the focal length, then you just find OA by 2 or OB by 2. It will be the given means focal length for the given convex lens. This is how, with these three different processes, you can find the focal length. Now we will come to the practical session. So as we have discussed in theory on the board, now we are here to explain the practical. So first of all, for the given convex lens, we need to find a rough focal length, and to find the rough focal length, this is the process by plotting the image of any distant object by this method. So here we have taken a lens holder. Along with the lens holder, we have taken a screen and a measuring scale. By adjusting the lens in the measuring scale, we are forming the distance, the image of the distant object. We can get the rough focal length. So from the experiment, we are able to see the rough focal length of the given convex lens is approximately 11.8. So with the, I tell the sir to show the, so you can see it is approximately 11.8. If you will see how to see whether the lens holder is showing the correct focal length or not. So the better thing, wherever you are able to see the image distance proper, after that you push little bit ahead or little backward. And if by putting ahead little, if it is the image is appearing blur, it means reaching to the same point where it will give the correct rough focal length. And here the image is pretty clear. So I think the revised one we can take that 11.1. 11.1 is the rough focal length of the given convex lens. So as I said, that first of all we need to check whether the given apparatus, that is optical bench, is completely horizontal with the surface or not. To see that, lot of process is there, but the best to follow. You decide 3 or 4 positions of the upright and just try to find out the height from the tabletop. As it is visible from here, that it is showing approximately 11 centimeters from the tabletop. If we will check here, or from this side, if suppose we are checking, it is approximately 11, and at the end is also approximately 11. So it means somehow it is parallel, and to see that we can also see with the one eye like this, that whether it is parallel or not. If we are confirmed that it is parallel, then we start with our second step. To get the better result, first of all, the center of the lens must coincide with the tip of the uprights. To measure means to see that whether it is correct or not, we can measure the height of the center of the lens with this, which is approximately, it is giving 15.5. so with that we can measure its height, whether it is 15.5 or not. If its tip is 15, so little bit we need to change, or in the second process also we can do. Afterwards also we need to check whether it is 15.5 or not. This is okay, 15.5. This we need to little bit up with 0.5 centimeter. Now we will set the position of the object as we got our rough focal length as 11.2. that we note down in our copy. So for our experiment, we have arranged the object pins lens holder. So object pins image distance, its placement is showing 22.4. the lens holder is kept at 50 centimeter. So it is showing 50 centimeter. Once again I want to show you the position of the object pin, that is at 22.4 centimeter. The lens you have seen 50 centimeter. Now the image pin we will set in such that all the three will be in the same line. And the most important thing, the tip of both the pins and the lens, center of the lens, they must lie in one line, that is on the principal axis. So first of all, I will tell my camera person to come here and to show that how means even though all the uprights and the lens are in one line, but still if we will move our eyes left and right, then we are seeing that both the object pin and image pin, which are coinciding tip to tip, but they are not moving together. You can see if we are moving slowly from left to right, you see the tip of the image pin and object pin, they are not moving together. Now I will adjust. Now you are seeing adjusting the image pin by doing forward and backward. You are able to see both the image pin and object pin, they are coinciding tip to tip. And when you are moving your eye from left to right, you see the object pin and the image pin, in which is showing inverted, both are moving together. This is called removal of parallax. When they were not moving together, it was parallax. But when they are removed, parallax is removed, then they are moving together. I just want to clear one thing. If I'll tell my camera person to show the camera towards me, that when we see one object just behind the other object and they are separated by a certain distance, then when we can say that they are in one line. Sometimes if we will close our left eye, its position is different, with right eye its position appears different. This effect is known as parallax. So when they are coming in line, when we can say, if by moving our left means eyes from left to right, if both are moving from tip to tip together, it means now parallax is removed. It means now both image pin and object pin are in one line. And it happens when two objects are in line but they are separated by a longer distance. Now by removing the parallax, we can note down the image pin, this position of the image pin, position of the object pin, position of the image pin, position of the image pin. Yes, we will note down in our copy like this. You can see here how we are noting it down. The object pin we have already noted down 22.4. The position of the lens is fixed at 50 centimeter, and you see as the least count of the optical bench is 0.1 centimeter. So whatever data we will write, even if it is round figure like 50, but we have to write as 50.0. So this is the way we have to write in the lab manual. Now we will see the position of the image pin here. I'll tell you the position of the image pin. It is showing around 67.1. So we will note down the image pin as 67.1. Now, so as you will see that we got the image distance by subtracting from length, position of lens and object, that 27.6 centimeter. The image distance we are getting 17.1. So similarly we can take 5 more observations by keeping the object between f and 2f and beyond 2f, so that we can get the correct value of image distance. And then means the process whatever we have used, which I have shown in our explanation, by using those process you can plot the graph, and then you can find the means focal length with the help of the graph. Now to know how to plot the graph, that I will explain in my second video, that the process of plotting the graph and how to get the focal length of the lens. Thank you.